This is Lecture 2, Review of Collecting and Describing Data. By the end of this lecture, you should be able to construct an operational definition of a variable, read data in SPSS, classify a dataset based on its unit of analysis, identify a variable's level of measurement, calculate and interpret the mode, median, and mean of a variable, construct and interpret a bar graph and histogram of a variable, and interpret the standard deviation of a variable. In the previous lecture, I briefly reviewed the basic steps in conducting a statistical analysis in political science research. Before I go into more detail on how to conduct statistical research in political science, first I need to teach you how to measure concepts and variables. If you do not know how to measure concepts and variables, you will not be able to conduct any statistical analyses. Hence, the first part of this lecture is all about collecting and measuring data. Political scientists study concepts such as liberalism and conservatism, and equality and inequality. These concepts are not tangible. You cannot touch them or hold them in your hand. You can't see them. You cannot hear them. Nevertheless, we know these concepts exist. They exist as mental constructs. Since these concepts are mostly mental constructs, we have to make sure we have a good definition of what they are if we want to measure them and collect data on them. For example, we may have a general idea of what war looks like. Two states may use physical force against each other. They may destroy each other's property, and there may be battle deaths. However, not all conflicts between states are wars. Sometimes two states will have a single battle in a single day, and the conflict will end. Is a one-day conflict a war? Not really. So how do political scientists distinguish between wars and short-term conflicts? One way is to use battle deaths as a criterion. The Correlates of War dataset classifies any conflict between states with 1,000 or more battle deaths as a war. In this part of the lecture, I will show you how to define concepts so they are measurable. When we measure concepts, we start by developing an operational definition. An operational definition tells us specifically how the concept is measured. The operational definition starts with the unit of analysis. The unit of analysis tells us who the subjects of the dataset are. Is it individuals or groups being measured, and when? The operational definition also includes the values the variable takes, what those values mean, what we have to do to observe in the real world to determine the value each observation takes, and the source of the data. Here's an example of an operational definition for a democracy variable. The unit of analysis is countries in 2017. The values the variable can take are 0 or 1. A 0 means a country is a non-democracy, and a 1 means a country is a democracy. In terms of what we have to observe in the real world to determine the value each observation takes, if leaders are selected in free and fair elections, where every adult can participate and the rules do not favor one party over the other, and leaders must face re-election at fixed intervals, the country is coded as a democracy. Otherwise, it is coded as a non-democracy. And the source of the data is the CIA World Factbook. Now I'm going to go through the steps of writing an operational definition. The first step in writing an operational definition of a variable is identifying the variable's unit of analysis. Recall that the unit of analysis tells us who we are measuring. Is it individuals? Is it groups? When do they exist? We can collect data from many different types of units. In terms of individuals, we could collect data from citizens, survey respondents, students, candidates, donors, legislators, executives, and judges. In terms of groups, we could collect data from political parties, interest groups, insurgencies, juntas, personal dictators, countries, and international organizations. In terms of when, we could collect data on a single day, over months, years, decades, or centuries. Using our democracy variable as an example, our unit of analysis from the definition was countries in the year 2017. The next step is establishing the specific observable criteria for your variable. For example, if we were measuring democracy and we wanted to measure elections, we would specifically examine whether a country has free and fair elections, where every adult could participate and the rules do not favor one party over the other. In addition, we would want to make sure leaders are held accountable. One observable and measurable way leaders can be held accountable is having to face re-election at fixed intervals. The next step in creating an operational definition is identifying the values your variable will take and what those values mean. For example, with our democracy variable, we can make a rule that when we identify a country as democratic, meaning it has free and fair elections and leaders face re-election at fixed intervals, we can give it a value of 1, and all other countries will receive a value of 0. The last step in creating an operational definition is identifying your data sources. Your data sources tell you whether your subjects meet the specific observable criteria in your variable. We can either use data we collected, which is called primary data, or use data that other people have collected, which is called secondary data. If we wanted to collect primary data, we would use information from news reports, government documents, surveys, or experiments. There are lots of places we can collect data from. Of course, there are also a lot of political science related data sets out there that other scholars have already created, so often it's just easier to use data other people have created instead of creating our own. So in our previous example, we stated that we would classify a country as democratic if it had free and fair elections where every adult could participate and the rules do not favor one party over the other. In addition, leaders in the country had to face re-election at fixed intervals. We could use the CIA World Factbook as a data source in this case to determine if different countries throughout the world meet these two criteria. The variable we created would be a primary source as we collected it. After we develop our operational definition, we can enter the data into a statistical software program. In this class, we will be using a program called SPSS to analyze our data. In SPSS, in the Data View tab, you can enter in the data for your data set. We will talk more about this in the labs when we get to them. The first thing you should know about SPSS is that the column headings identify the variable names. Typically, the first couple of variables in your data set should identify your data set's unit of analysis. So in this data set, the subjects of the data set are countries and the year is 2017, so we know the unit of analysis for this data set is countries in the year 2017. The subsequent column headings should be the names of the variables. So the first variable in this data set is GDP per capita. Next, the rows are where you enter in the data for the individual observations. So for observation 5, the country is Luxembourg, the year is 2017, and the value for GDP per capita for Luxembourg in 2017 is 109,100. Also note that the number of rows in SPSS tells you how many observations there are in the data set. Each observation includes an individual subject with values for each variable. So in this data set, there are 10 rows, so there are 10 observations. After we write our operational definitions and collect our data, we can classify what kind of data set we have. This classification will be based on our unit of analysis. Recall that the unit of analysis tells you who the variable applies to and when the subject existed. Based on the unit of analysis, you can classify your data set as either a case study, cross-sectional, time series, or cross-sectional time series variable. This chart here can help you determine what kind of variable you have. If your variable only has one subject and you only have a few observations for that subject, then you have a case study. An example of this would be studying democracy in the U.S. in 2017. There would only be one subject, the U.S., with a couple of observations in 2017. If your variable only applies to one subject, but you have multiple observations for that subject over time, then you have a time series variable. An example of this would be studying democracy in the U.S. between 2001 and 2017. There would only be one subject, the U.S., with multiple observations between 2001 and 2017. If your variable applies to multiple subjects, and you only have one observation per subject, then you have a cross-sectional variable. An example of this would be studying democracy in all countries throughout the world in 2017. there would be multiple subjects, all countries in the world, with one observation each in 2017. If your variable applies to many subjects and you have multiple observations per subject over time, then you have a cross-sectional time series variable. An example of this would be studying democracy in all countries throughout the world from 2001 to 2017. There would be multiple subjects, all countries in the world, with multiple observations between 2001 and 2017. Going back to our democracy variable example, our unit of analysis was countries throughout the world in 2017. In our variable, we would have observations for many subjects, all countries in the world, with one observation each in 2017, so this would make the variable cross-sectional. In this part of the lecture, I'm going to show you how to classify a variable based on the values the variable can take. You can classify a variable as nominal, ordinal, interval, or ratio level. Remembering the word noir is an easy way to remember these four terms, as the letters in the word noir are the first letters of these four words. Noir means black in French. Nominal level variables divide the subjects or observations in your variable into different categories. The categories are exhaustive, meaning that you included all possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your data set into one of the categories. And note, while there is a numerical difference in categories, there is no inherent order in the data. One category is not greater than another. For example, if you were collecting data on voters' party identification, you would have 3 different categories in your data: Republican, Democrat, and Independent. These categories are mostly exhaustive, as they capture the 3 main party identifications in the U.S. These categories are also mutually exclusive because a voter cannot be classified into categories such as Democrat and Republican. And even though these categories have numerical values, there is no inherent order in the variable. Even though independents are given a 2, they are not greater than Democrats a 1 or Republicans a 0. Ordinal level variables also divide the subjects or observations in your variable into different categories. The categories are exhaustive, meaning that you included all possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your data set into one of the categories. In addition, there is inherent order with an ordinal level variable. For example, many surveys ask respondents about the extent to which they support a candidate. The surveyors divide the support answers into numerical rank ordered categories such as strongly oppose a -2, oppose a 1, neutral a 0, support a 1, and strong support a 2. As you can see, the least support has the lowest value, -2, and as the respondent's support increases, the value goes up by 1. However, note that while there is inherent numerical order in the data, the spaces between the categories are not inherently fixed. A survey respondent might feel that there is a huge difference between strongly oppose and oppose, but a small difference between oppose and neutral. Interval level variables are ordered. The spaces between the categories are fixed. For example, the spaces between 1 and 2 equal the same distance between 2 and 3, 1 unit. But with interval level variables, there is no true 0. Ideology could be an interval level variable. You could have a continuous variable that ranged from 0, extremely liberal, to 5, moderate, to 10, extremely conservative. But the 0 in this case is an artificial 0. We could have moved the scale from -5 to 5, and 0 would become moderate, and it would not fundamentally change the nature of the variable. Last, ratio level variables are ordered, the spaces between the categories are fixed, and ratio level variables have a true 0. Military spending is a ratio level variable. Military spending ranges from 0 to any positive value, and 0 is substantively meaningful. It means 0 military spending, so the variable has a true 0. Next, I'm going to show you how to use basic statistics to describe data. First, I will discuss measures of central tendency. Central tendency is just another way of saying the average or typical case of a variable. There are 3 measures of central tendency: the mode, median, and mean. The mode is the most common or most repeated value in the variable. In order to find the mode by hand, you arrange the values from the smallest to largest, then you find the most repeated values in the dataset. I will start with a simple example to demonstrate how to calculate the mode of a variable. Imagine you had a variable that took on the following values: 10, 15, 2, 6, 2, 10, 10. First, arrange the values from smallest to largest: 2, 2, 6, 10, 10, 10, 15. Find the most repeated value, 10. Since 10 is the most repeated value, it is the mode. To demonstrate how to find the mode with an actual variable, I will use the Commonspace scores from the 106th Congress. Commonspace scores measure House members' ideological positions by using roll call votes. Commonspace scores range from -1 to 1, with values less than 0 being liberal and values greater than 0 being conservative. In this particular example, I arranged the data from the smallest to the largest value. There were two modes in the data. There was a mode for -0.374, and that was for Democrats, and a mode for Republicans, 0.359. In both cases, there are 6 observations with the value of -0.374 and 0.359. There are no values in the data set where there are 7 or more observations that share that value. So the two modes are -0.374 and 0.359. The second measure of central tendency is the median. The median is the minimalist value of a variable. It cuts the variable in half, with the lowest 50% of values on one side and the highest 50% of values on the upper side. To find the median by hand, you arrange your variable from smallest to largest value. Then you find the median observation number. The position of the median when you have an odd number of observations is equal to the number of observations plus 1, and that value divided by 2. The median observations value is the median. I will start with a simple example to demonstrate how to calculate the median of a variable. Imagine you had a variable that took on the following values: 10, 15, 2, 6, 2, 10, 10. First, arrange the values from smallest to largest: 2, 2, 6, 10, 10, 10, 15. Then count the number of observations: 1, 2, 3, 4, 5, 6, 7. There are 7 observations. Then find the position of the median, which is equal to the number of observations plus 1, and that value divided by 2. So 7 plus 1 equals 8, and that value divided by 2 is 4. So find observation 4. 1, 2, 3, 4. Observation 4 takes on a value of 10, so 10 is the median. For a more realistic example on how to calculate the median, I will use the Commonspace score example. In our Commonspace score example, there were 437 observations. 437 plus 1 is 438, and 438 divided by 2 is 219. So the median observation number is 219. I have arranged the data from the smallest to the largest value. Observation 219 takes on a value of 0.137. So the median is 0.137. If the median House member has a Commonspace score of 0.137, who do you think controlled the House of Representatives, Republicans or Democrats? It was Republicans. Recall that Commonspace scores greater than 0 indicate a House member is conservative. The median tells us which House member is in the middle of all the House members. In this case, the middle House member has a Commonspace score of 0.137, which indicates that they are conservative, indicating that Republicans control the House of Representatives. The third measure of central tendency is the mean. The mean is the sum of a set of values divided by the total number of observations. Formally, the equation looks like this. X bar means the mean of X. Any variable with a bar over it indicates that it is the mean of the variable. The Greek letter sigma, capitalized, means the sum of. In this case, it means the sum of all the observations in X, and N means the number of observations. I will start with a simple example to demonstrate how to calculate the mean of a variable. Imagine you had a variable that took on the following values: 10, 15, 2, 6, 2, 10, 10. First, you add all the values together: 10 plus 15 plus 2 plus 6 plus 2 plus 10 plus 10. That equals 55. Then you divide that value by the total number of observations. 1, 2, 3, 4, 5, 6, 7. So divide by 7. 55 divided by 7 is 7.9. The mean is 7.9. Now I will show you how to calculate the mean for a real variable. For our Commonspace score example, the mean of the Commonspace scores are the sum of the Commonspace scores divided by the total number of observations. I will do this by hand. The sum of the Commonspace scores was 21.788. The total number of observations was 437. 21788 divided by 437 equals 0.05. The mean of the Commonspace scores was 0.05. So in sum, there are 3 different measures of central tendency: the mode, median, and mean. And all 3 measures give us different values, as in the Commonspace score example, leading us to draw different conclusions about the average or typical case of a variable. So when do we use these 3 different measures? If we are examining a nominal level variable, we should only use the mode. Recall that the values of a nominal level variable have no order. The mode does not assume a variable has order, but the median and mean do assume a variable has order. Hence, with a nominal level variable, we only use the mode to describe the typical case of a variable because the mode does not assume we have order. With an ordinal level variable, the values of the variable have order, but the spaces between the values are not fixed. We can use the mode for an ordinal level variable because the mode simply tells us the most common value in the data. We can also use the median because we can order the data from smallest to largest and find the middlemost value. We can also use the mean, but it is debatable whether it makes sense to use the mean for an ordinal level variable. The mean assumes the spaces between the variable are fixed, which is not always the case with an ordinal level variable. Nevertheless, social scientists often use the mean to describe an ordinal level variable. Next, recall that interval and ratio level variables are ordered and continuous. Hence, we could either use the mean, median, or mode to describe the typical value of these variables. A bar graph is a visual representation of how many observations in our variable fit into specific categories in our variable. As such, it is best used for nominal and ordinal level variables. To illustrate how many observations fit into each category, we use bars, hence why it's called a bar graph. When you construct a bar graph, you place the total number of observations or percent of observations on the y-axis and the category names on the x-axis. Then you add bars on top of the categories on the x-axis to represent how many observations fit into each category. This is a bar graph that represents the information from a polity 4 frequency distribution. The polity 4 variable classifies countries into autocracies, anocracies, or democracies. As you can see, the percent of observations is on the y-axis, and the category names are on the x-axis. Note that I placed the variable name below the x-axis as well. 20% of the observations were autocracies, so this bar on top of autocracies extends to 20% on the y-axis. 50% of observations were anocracies, so this bar on top of anocracies extends to 50% on the y-axis. And 30% of the observations were democracies, so this bar on top of democracies extends to 30% on the y-axis. To interpret this bar graph, we could just simply say 20% of cases were autocracies, 50% were anocracies, and 30% were democracies. Now I'm going to briefly describe how histograms are constructed. A histogram is just a special kind of bar graph for interval and ratio level variables. If we made a bar graph out of an interval or ratio level variable, then we'd have to put a category on the x-axis for every single value of the variable, which would be a lot of categories. With so many categories on the x-axis, the graph wouldn't be visually appealing or informative. So instead, we create categories or bins on the x-axis that represent a range of values for the variable. Then we count to see how many observations that have values that fit within the range of the values for each category. Hence, the bars represent the total number of, or percentage of observations in the variable that fit within a range of values for each category. Here's an example of a histogram of Commonspace scores from the House in the 106th Congress. Recall from the beginning of the lecture that Commonspace scores measure Congress members' ideological leanings on a -1-to-1 scale based on their voting behavior. As you can see on the x-axis, these bars do not represent specific values of a variable. They represent a range of values. This makes the graph more informative and visually appealing. If there was a bar for each Commonspace value, the graph would look very cluttered, messy, and hard to interpret. So what does this histogram tell us about the typical member of Congress? We could say something like, there wasn't a typical member of Congress. Instead, there were two typical House members in Congress, a liberal Democrat and a conservative Republican. About 42 House members were liberal Democrats here, and about 50 House members were conservative Republicans about here. Now I'm going to show you how to describe a bar graph or histogram for ordinal, interval, and ratio level variables using the following characteristics: center and range, number of peaks or modes, and skewness. The center of a bar graph or histogram is where the median is located. You can calculate this by hand or use SPSS to do it, which you will learn how to do in the next lab video. The range of a bar graph or histogram tells us the difference between the largest and smallest observation values. The simplest way to calculate the range of a bar graph or histogram is to take the value of the largest observation value and subtract the value of the smallest observation value from it. For example, in this bar graph, the center or median is 50, the range is 90, the largest observation value, minus 10, the smallest observation value, which is 80. The next characteristic of a bar graph or histogram that you should describe is the number of peaks and where they are. A peak is like a mountain peak. It creates a clear upward pattern in the data with other bars following that pattern and eventually clustering around it. To find a peak, draw a general outline on top of the bar graph or histogram. Here's a histogram of states' vote share for Gore in the 2000 presidential election. I drew a general outline on top of it. From this outline, I can see that there is one clear peak around 45. There is an upward trend to this peak that the other bars follow, and these bars are clustering around the peak. Here's a histogram of the Heritage Foundation's ratings of government spending. I drew a general outline on top of it. From this outline, I can see that there's a clear peak around 80. There is an upward trend to this peak that the other bars follow. It is like the bars are building stairs up here to the peak, and these bars are clustering around it. Here's a histogram of the UN's Gender Inequality Index for countries around the world. I drew a general outline on top of it. From this outline, I can see there are two clear peaks, one around 0.3 and one around 0.7. With this graph here, the upward trend to the one peak looks like stairs. There's no other distinctive pattern in this graph. With this graph here, the two upward trends look like two very distinctive mountain peaks, with bars clustering around both. Now, when you describe the peaks in the graph, you should know how many there are and where they're at. If there's only one peak, the graph is unimodal. If there are two peaks, the graph is bimodal. If there are many clear peaks, the graph is multimodal. And if there's more than one clear peak, note if the peaks are about the same size or if some are bigger than others. Also note, as this is a bit confusing, that calculating the mode by hand is different than calculating the mode or modes in a graph. Here's an example of a graph that is unimodal, with one mode at 50. There is one clear peak. Here's an example of a bar graph that is bimodal, with one mode at 0 and the other at 100. These are two distinct peaks, and the peaks are about the same size. Here's an example of a histogram that is bimodal, with one mode around negative 0.4 and one around positive 0.4, and the positive 0.4 mode is larger. The next characteristic of a bar graph or histogram that you have to describe is skewness. If a bar graph or histogram has a negative skew, the left side of the graph extends much further than the right side of the graph. If it has a positive skew, the right side of the graph extends much further than the left side of the graph. If there is no skew, the left and right side of the graph extend about the same amount from the center. You can fold it in half and the shapes will be the same on both sides. Here's an example of a bar graph with a negative skew, as the left side of the graph extends much further than the right. Here is a general outline on top. As you can see, the left side is extending much further than the right. It is extending in a negative direction, hence a negative skew. This is an example of a bar graph with a positive skew, as the right side of the graph extends much further than the left side of the graph. Here's a general outline on top. As you can see, the right side is extending much further than the left. It is extending into a positive direction, hence a positive skew. Here's an example of a bar graph with no skew, as the left and right sides of the graph extend about the same from the center. You could fold this in half and the left and right side would be the same shapes. Now I'm going to teach you an additional way to describe the distribution of a variable, the standard deviation. Consider these two histograms of two different variables. Each variable has the same mean, 50. Each variable has the same range, 0 to 100, so 100. And each graph has one peak. They're unimodal around 50. And each one has no skew. Yet the variables look distributed in different ways. If you examine the variable on the left, the distribution is more peaked around the mean of 50, meaning many observations take on values that are close to 50. But with the variable on the right, the distribution is more flat, with many observations taking values that are far away from 50. On the left, we would say there is very little variance, and on the right, we could say there's a lot of variance. We can calculate a numerical value that tells us by how much a variable's observations deviate from the mean on average. That value is called the standard deviation. I will briefly show you how to calculate it. You do not have to calculate it in this class, but you do need to know how it is calculated and how to interpret it. You start with the sample variance. The sample variance, denoted by S squared, is the sum of each observation minus the sample mean squared, and that value divided by the total number of observations minus 1. Note what is happening within the numerator of the variance. We take each individual observation and subtract the mean from it. In other words, we're trying to figure out how far each observation is from the mean. So imagine the mean was 29.4 and we have these two observations here. We're trying to figure out how far those observations are from the mean. Then we square the values. Squaring the values gets rid of negative deviations. So now everything is positive. Then we add all the squared deviations together. and divide by the total number of observations minus 1. This is very close to the calculation for a mean. Remember, the calculation for a mean is adding all the observation values together and divided by the total number of observations. This is very close to that. The resulting value from this calculation gives us the variance. Then we take the square root of the variance to get the sample standard deviation S. Remember when we squared these deviations from the mean? This made the numbers very large. By taking the square root, we bring the values down to a more realistic value, giving the values of the variable that we have. So sample standard deviation is just the square root of the sample variance. Now we can interpret the mean and standard deviation. To interpret it, we should start out by stating the mean of our variable. Then we would say, in our sample, observations deviated about standard deviation units from the mean on average. The units in this template just tell us what units our variable are measured in. So for example, imagine we had a life expectancy at birth variable for all countries in the world. The mean was 73 years, the standard deviation was 7.3 years. Applying our template to it, we could say, the mean of life expectancy is 73 years. Observations deviated about 7.3 years from the mean on average.